All right, folks, so I want to go over something now called Fermat's theorem. And this is a useful theorem that we're going to need it to build Rolle's theorem, and we'll use Rolle's theorem to build the mean value theorem. So we're laying the building blocks for one of the big results of calculus. This is Fermat's theorem. Be careful for those of you who know your math floor. This isn't Fermat's famous last theorem. This is just another math theorem. Okay, it's not the famous one that was solved by Andrew Weil. So what does Fermat's theorem say? Okay. It says, suppose f has a local maximum or minimum at some point c. Okay. There's a lot to unpack there. We've got a function. Okay. At some point c on that function, we know we've got a local maximum or a local minimum. By the way, we actually know one other thing, because our author said that local maximums and minimums can only occur at interior points, so we know that we're talking about an interior point on the function. Okay? So that's the first thing. Okay, if we have that, and second, if the derivative exists, then the conclusion of Fermat's theorem is that the derivative must be 0 at that point. Okay, so I'd like to see if we can get an understanding of Fermat's theorem by looking at a graph here. Let's see how we can do making this graph. Let's go like this, and so here we've got a function. It's kind of an interesting looking function. Let's call it f of x. Okay. So first of all, we're only going to consider interior points. So we're not going to consider this. Because we're only interested in local maximums, minimums. Those have to occur at interior points. So let's look at the first condition. Let's find out where f has local maximums and minimums. Well, f has a local maximum right here, and it has a local minimum right here. It also has a local minimum right here and a local maximum right here. Okay? So again, in all of those instances, what am I able to do? If I'm going to call it a local max or a local min, I've got to be able to draw a neighborhood around it so that for all y values in that neighborhood, if it's going to be a local minimum, it's got to be the lowest point around. Okay? Or if it's going to be a local maximum, when I draw the neighborhood, now careful, can I draw my neighborhood out here? Nope. Better move it in a little bit. Okay? For all y values that I plug in, if this is going to be a local maximum, it has to be the greatest of the y values. Okay, that's just a quick summary. Okay. So we can do the same thing here. We've got a local maximum, and the same thing here. We've got a local minimum. Let's go ahead and call that C1. We'll call that C2. We'll call this C3, and we'll call this C4. Okay. So let's see how Fermat's theorem either applies or doesn't apply at each one of these points. So Fermat's theorem, and first we say, let's find where we have local maximum minimums. We found those c values. Then the second condition is that f prime of c exists. Okay? If we've satisfied both condition 1 and condition 2, then Fermat's theorem says that the derivative must be 0 there. Okay? So let's look at what I've called c1. Okay? Well, at c1, we do indeed have a local, in this case, maximum. And does the derivative exist at c1? Yes. Notice this function is nice and smooth around c1. So we can take the appropriate limit that we need to calculate the derivative. So f prime of c does exist. So what is the big conclusion of Fermat's theorem? At that point there, the derivative must be 0. Well, we look at the graph, and sure enough, it is. Okay? Similarly, if we look at what I've called c2, in this case, c2 gives us a local minimum. It is differentiable there, and what is the derivative? The derivative is 0. Okay. Let's look at what I called point C3. At C3, I meet the first of the two conditions for Fermat's theorem. I've got a local maximum or minimum. In this case, it's a local maximum. Okay. The second condition, though, says the derivative must exist. But what do we know there? Well, there I've tried to draw. It looks like, I hope it looks like a corner. If it looks like a cusp to you, that's okay. It'll still work. But it's supposed to be a corner. And at that corner, it's not differentiable. Remember, that was one of our conditions for, that was one of our scenarios that we saw where a derivative wouldn't exist, even though we were continuous. So even though we're continuous at C3, the derivative does not exist. So Fermat's theorem does not apply because we failed to meet this condition. So let's just say here, Fermat's doesn't apply. I'll put DNA for does not apply. Okay. Likewise here, Fermat's does not apply. So even though I have a local minimum at C4, since it's not differentiable because of that cusp, then we can't make any we can't conclude that the derivative is 0, and that should make sense. Okay. So what does Fermat's theorem say? It says that the phenomena that we see in this graph are true universally. So it's not limited to this graph that I drew. It is always true that if you have a local max or min in a place and the derivative exists there, then the derivative must be 0. Okay, number 12 asks the next question. Is the converse of Fermat's theorem true? So let's go back and look at Fermat's theorem. Okay, so Fermat's theorem said if we have a local max or min at some c value and the derivative exists, then the derivative must be 0. So the converse of that, okay, which is not, we'll find out is not true, but let me just say what the converse would be. The converse would say if f prime of x equals 0, does that imply that f has a local max or min at that point? That's what the converse would say. Well, it turns out that the converse is false. Okay. So let me give you a graph that illustrates why the converse is false. Let's look at the graph of, let's look at the graph of the cube root, or excuse me, the x cubed function. So here's a graph of the x cubed function. Okay. And notice what happens at x equals 0. At x equals 0, what is the derivative? So f prime of x here equals 0. Okay. So here we have a place, let me put that in a different color. Here we have a place where the derivative is 0. Do we have a local max or min there? No, we don't. We've just got what's called an inflection point there. We'll talk about that later. But here we see an example where the converse of Fermat's theorem is not true. So just because the derivative equals 0 does not mean you're going to have a local max or min. Remember what Fermat's theorem said, though. It said if you have a local max or min, and the derivative exists, then that derivative must be 0.